Thank you so much, Aaron. Well, as mentioned by Aaron, Rajith is unfortunately not able to present today because of the internet connection issue at the place. So I think it kind of reflects the importance of what communications people are doing. So it is my great pleasure to have this opportunity to present our work at the IEEE ComSoc workshop. My name is Tian. I'm a research fellow working at the University of Melbourne. Today, I would like to talk about our work on integrated sensing and communications, and more specifically, on designing constant modulus ISAC waveforms. This work is funded by the Australian Research Council through a discovery project. So, before going to the research, I would like to first thank and introduce our team to you. The university, here's the University of Melbourne team with Rachita and Jamie leading this project. We have two very experienced radar experts, William and Robin, and research fellow Shalanika and myself, who have been working on it from the beginning of my PhD. We also have two experts outside of the University of Melbourne, Peter from Victoria University of Wellington and Bashi from University of Southern California. Just give me a second. So now going back to the research topic, I think most of you know what ISAC is, but still want to give a short introduction to it. So conventionally, communications and radar sensing were designed separately in isolation, addressing domain-specific challenges. More specifically, in a communication system, transmitter generates a signal based on the incoming data, and the receiver tries to decode the data from the received signal. On the other hand, in a radar system, the transmitter usually sends a deterministic signal to the environment, and the receiver, which knows what is transmitted, tries to learn information of the target, or more generally, the environment, by comparing the received signal with the transmitted one. In recent years, there have been increasing interest in the integration of communication sensing. I think this is partially motivated by the requirements of various applications in future wireless networks such as IoT, which both sensing and communications play very significant roles. To achieve such integration, there are various open challenges. One of the most important challenges to be addressed is the design of waveforms that are capable for simultaneous data transmission and radar sensing. Generally speaking, ISAC waveform design methods can be classified into three categories. The radar-centric design focuses on embedding laser points here. So the radar-centric designs focus on embedding data into traditional radar waveforms such as linear frequency modulation or so-called chirp-based waveforms. On the other hand, communication-centric designs try to integrate the sensing functionality into existing communication system or waveforms. Examples include those using OFDM and those designing the preamble of the 802.11 standard for sensing. There also exist methods which do not rely on existing waveforms. They're usually designed from ground up by solving resource allocation or optimization problems to take care of the performance from both aspects or achieves sort of a trade-off between them. This is called co-design. It is worth pointing out that multi-carrier waveforms, such as OFDM typed ones introduced here, have been considered good candidates for ISAC, mostly because of the superior communications performance and the maturity in the system design. Even in the third category, there are works focusing on allocating resource among time frequency blocks, which in turn results in multi-carrier waveforms. However, multi-carrier waveforms suffer from the problem of high peak-to-average power ratio values. Actually, this problem has been discussed a lot in traditional communication systems and also has attracted interest in recent years from the ISAC perspective. So why is PAPR important? One major reason is the existence of nonlinear devices at RF front end. So a good example is the power amplifier. Here's the input-output relationship of a power amplifier. It is approximately linear in the low power region, but gets saturated once exceeding the saturation point. So due to the very high attenuation in millimeter wave bands, to achieve a sufficient SNR, power amplifiers at transmitters usually operate at or at least close to the saturation point. If a waveform with a very high peak-to-average power ratio passes through, it will suffer from the clipping effect and get severely distorted. From the radar perspective, even if we design a waveform with perfect radar sensing capabilities, if it gets distorted, these ideal properties no longer exist. This is partially why constant modulus waveforms with a unit baseband PAPR are used a lot in traditional radar applications. From the communications perspective, like for commonly used high PAPR waveforms such as OFDM, the nonlinear distortion can lead to interference between adjacent frequency bands and also distortion within each band, resulting in an increase in the bit error probability. Although there exist various PAPR reduction techniques, such solutions introduce additional overheads to the system, hence increases the complexity, cost, or power consumptions. So we can see that low PAPR is important from radar and comms perspectives. In other words, important for ISAC applications, especially those overweigh power and cost efficiency against spectral efficiency. This motivates our work on designing constant modulus ISAC waveforms with a unit baseband peak to average power ratio. So we have proposed various designs, but today I'll focus on one of them, the frequency permutation-based scheme. The idea of using frequency permutations is initially from conventional stepped frequency radar waveform. The most commonly used stepped frequency waveform is the one with a linearly increasing frequency sequence. Here is the signal model. The waveform has m single carrier pulses, where the center frequency of each pulse is increased by delta ref from the preceding one. As such, the resulting frequency pattern is linearly increasing, which can be viewed as a discrete approximation of the well-known frequency chirp. So such a waveform has various advantages in terms of radar. First of all, it has a single carrier in each pulse, and no amplitude modulation included, which means it has a unit baseband PAPR. Secondly, such a waveform, if the number of elements, number of pulses in the waveform is large, it occupies a very large time bandwidth product, which leads to good delay and Doppler estimation capabilities. Now, it's good in terms of radar, but what if we also want to use it for communications? Obviously, linear step frequency cannot be used for data transmission because it only has one single frequency pattern. To embed data into it, in this work, we consider using permutations of the frequency sequence. The signal model looks very similar to the linear step frequency, except for the frequency pattern. Instead of the linearly increasing sequence of the available m available frequencies, the novel scheme considers all m factorial permutations of these m frequencies. So such a scheme allows us to transmit log 2 of m factorial bits per waveform. Well, we should round it down to the closest integer. Due to the time limit, I will focus more on the communication side, but I do want to mention one thing regarding the radar sensing capability. The use of frequency permutations ensures a deterministic control of the time bandwidth product, regardless of the data embedded. And the value of the time bandwidth product is exactly the same as the stepped frequency radar waveform if the same waveform parameters are used. In other words, this novel design is able to transmit data while keeping the good delay Doppler sensing capabilities as a traditional radar waveform. Now let's take a look at this communications performance. Since there are m factorial possible waveforms, you might think the mapping between the data bits and corresponding waveform is impractical for large m, as it requires a very large lookup table. However, thanks to a combinatorial transform called the lemma code, the use of lookup table is actually not required. So what it does is it first obtains symbol, or what the decimal representation of the bit sequence. Then the integer is presented in the factorial number system by iteratively dividing it or the quotients by 1 all the way up to m, and then puts all the reminders in the reverse order. So, well, for example, if m is equivalent to 4, and if m is equivalent to 4 and the decimal representation of the bit sequence is 5, we first divide 5 by 1, resulting in quotient 5 remainder 0. And we divide the quotient 5 by 2, resulting in quotient 2 remainder 1. And we repeat the step until the fourth m equals fourth iteration, and put the reminders in the reverse order, 0, 2, 1, 0, which is the factorial representation. Next, we map the factorial representation of length m to the frequency sequence by iteratively taking the frequency with the index given by the factorial representation out without replacement. So the example is here, and since m equals 4, we have 4 frequencies, if not all the way up to f3. The first index is 0, so we take out f0, then the sequence becomes f1, f2, f3. Second index is 2, so we take 0, 1, 2, f3 out, and then etc. We do follow these steps, and then resulting in frequency sequence, if not f3, f2, f1. It has been shown that both steps of the transform have a linear complexity with respect to m, hence the mapping is very efficient. We also analyze this communications receiver performance. We derive the maximum likelihood symbol detector for this novel modulation scheme under the simulcase for various statistical block fading models. So here's like a very typical received signal model with block fading channel, the transmitted signal, and the noise. So the maximum likelihood is given here. Again, kind of similar to what we mentioned previously, you may question the complexity of the maximum likelihood detector if we have to perform an exhaustive search over all m factorial possibilities. But we propose an efficient implementation of the maximum likelihood detector using the Hungarian algorithm. So the Hungarian algorithm is used for task allocation problems where m tasks should be allocated to m workers while minimizing the total cost. This is actually very similar to what the symbol detector needs to do, that is allocating m frequencies to m time slots without repetition while maximizing the log likelihood. The Hungarian algorithm allows us to solve this time frequency allocation problem with worst case complexity big O of m cubed, which is obviously more efficient than the exhaustive search, which is big O of m factorial. We then analyze the symbol error probability of this maximum likelihood detector by deriving the union bounds and the nearest neighbor approximation. So I put the expressions here for completeness, but I will not go through the derivations. Here are several numerical examples showing the accuracy of the analysis. So we choose multiple waveform and channel parameters. M is the length of the frequency sequence, and K is the Riemann K factor. For all sets of parameters, we observe that the union bound given by red tightly upper bounds the empirical error rate given by blue, especially in the high signal-to-noise ratio region, while the nearest neighbor approximation almost always closely follow the empirical error rate. Now, finally, I would like to talk a bit about other constant modulus Isaac waveforms we have designed. The frequency permutation scheme is like the starting point of our other designs. So one problem of the frequency permutation scheme is its relatively low data rate, hence various methods are considered to improve it. So we first consider using PSK on top of frequency modulation and show that the data rate is improved with little impact on its good radar properties. Nevertheless, this introduces extra complexity to the symbol detector. So the problem of complex symbol detector can be solved by using housewise independent FSK-based waveforms, which increases the data rate while decreasing the detector complexity, but with a sacrifice in the stability of the radar performance. We then consider using extra phase code on top of that to control and optimize the radar performance. On the other hand, for extreme low data rate applications, we also propose schemes which choose particular subsets of frequency permutations. This allows for improving either the symbol error rate or the radar performance by sacrificing the data rate. This is here are some publications we have. the two above are related to frequency permutation work I focused on today, and while the others are related to the works I mentioned on the previous slide. So I think that's all for this presentation. Thank you so much for listening.